Thanks for joining me for this session on reacting to the future of application architecture. My name is Grace Jansen, I work in IBM in the UK, and I'm a developer advocate. So, to look forward to the future of application architecture, first let's take a look at where we come from and our evolution so far. So when we first started building applications, we were using this monolithic style of application architecture. And that was fine for our small applications. They had relatively small amounts of traffic going to them, they had small data requirements, and generally it was alright that we could update that data over fairly long periods of time. So we could do things like batch processing and have that data updated overnight. But then we had this move to microservices so that we could really separate out and distribute our different services out to those microservices. And this move from monolithic to microservice enabled us to achieve sort of solutions to problems that we'd previously been experiencing. So it enabled us to easily add new features, to deploy fairly small parts of an application rather than having to deploy the entire application again, to be able to isolate failures, and essentially sort of distribute out and decouple the different aspects of our applications. But this architecture type still has problems. It's not perfect. We can still go to a website, put things in our shopping trolley, go to checkout, and find that items have disappeared because someone else bought them first. I can still lose a seat reservation when I'm booking the cinema, and on Black Friday, sometimes with like entire websites, I still can't access it because they just can't deal with the fluctuating load and the huge quantities of traffic going to their sites on those specific sort of sale days. And our modern users expect a lot more from our applications than they previously did. Users expect to be able to have sort of instant reactions to any actions that they perform on the website, and to be able to get the same service from the website or the application regardless of the day of the week, time, season, etc. So how can we tackle these new demands and increased expectations that users are putting on our applications? Where do we go with our evolution? Well, I come from a biology background, so I looked to nature as my inspiration. And so looked around and thought, is there a natural analogy to microservices that exhibit the behaviors that we want to see in the future of our applications? And I came across bees. So bees are an amazing analogy to microservices. Bees are, well, a beehive is a system of individual bees, and each bee has their own responsibility and roles, but they work together for the benefit and the good of the hive as a whole. And they work together for this core system. So it's just like microservices. Each microservice has their own role to play within the system, but it works together to make the application whole. And bees have been evolving the behaviors that we want to see in our own applications for millennia. In fact, the oldest bee fossil that was found, which was discovered back in 2006, is 100 million years old. So literally for millennia, they've been evolving and making these behaviors as efficient as possible. So can we use them for inspiration when it comes to our applications? So I promise you this is not just a rant about bees and their awesomeness. I'm going to take you through 3 examples of bee behavior that we'd like to see mimicked in our own applications, and then I'll show you how it links to software afterwards. So the first behavior is food foraging. So beehives have a really sophisticated social structure, which basically means each bee within the hive has their own role, and there are loads of different roles you can perform within the hive. So you can be a nurser bee, a guard bee, a scout bee. There's even air conditioning bees, undertaker bees. There's a huge array of roles. Now the one that we'll be looking at in this behavior is a scout bee. Now the role of a scout bee is to basically go out of the hive and find food, so find a flower. Once they've found a food source, found a great flower, the scout bees then immediately rush back to the hive to tell the others. And to do that, they head to these dedicated dance floors in the hive. And when they're at these dedicated dance floors, there'll be listener bees sort of gathered around the dance floors who will watch the scout bees dance on this dance floor. So the scout bees will essentially wiggle their bottoms around in different directions to communicate really complicated instructions about the food source. And they can communicate a huge array of information, including where the food source is, how far away it is, how long it will take to get there, even the wind speed on the way to get there. Now, the important part are these listener bees. So these independent observer bees are essentially listening and waiting for the scouts to dance. Now, as soon as those listener bees have the minimum amount of information they need, they immediately dash off to that food source to get the food. Now, it's really important that they're extremely responsive to the dance moves and to the information they're being given. And it's really important that they reach that food source as soon as they can. For bees, it is literally a life or death situation in terms of being as responsive as possible. Because if another group of bees from another beehive reach that food source first, by the time they get there, all the food's going to be gone. So it's essential that they respond to this and are responsive, extremely responsive to the scout bees. And we want this in our own applications. Okay, maybe it's not a life or death situation most of the time in our applications, but we want our applications to mimic this level of responsiveness. We want our applications to be able to give users the feedback and the actions and the response to their actions as soon as possible. Just like bees, we want them to be highly responsive. The second behavior is, okay, what happens when the queen bee dies? Now, there's only ever one queen bee within a hive, and her role is to produce all of the babies for the hive. So without a queen, there's no babies, no future of the hive. So arguably, she is the most important member of that bee society. So what happens when there's a potentially catastrophic failure of the queen dies? Does the hive crash? Does it stop working? Do all the worker bees go into like a craze? No. The worker bees continue on as normal because they have an innate trust in the system that that queen bee, that essential member of that hive, will be replaced. So what happens is when the queen is alive, she emits these pheromone or chemical signals. Then when she dies, those chemical pheromone signals disappear. So the nurser bees that have been looking after her realise and they spring into action to replace the queen. So these nurser bees pick about 4 or 5 larvae that haven't hatched yet, and they start feeding them royal jelly. And it's this royal jelly that turns them specifically into a queen bee rather than any other type of bee. When the first one of those larvae hatches, she then becomes the queen bee. Brutally, she then murders the others, but eventually she then mates and becomes the queen bee, and the hive can continue on as it was before. In the meantime, all of the other bees, like the nurser bees, the undertaker bees, the scout bees, the guard bees, they continue on as normal, even in the face of this potential failure. So bees in this regard are extremely resilient. And we want our applications to be resilient in the face of potential failure as well. So we need to have the same sort of decoupling and the same process in place of being able to deal with these potential failures and enable our system to be resilient so that it can continue when these potentially catastrophic failures occur. So we also want to mimic the extreme resiliency of bees. Now the third and last behaviour, I promise, is bees at war. Okay, I was having a little bit too much fun with my mum with the diagrams. But what happens when the hive is under attack? So as I mentioned, there are loads of different roles that bees play within the hive. One of those is guard bees. As the name suggests, guard bees essentially protect the hive from any invaders, predators, etc. So actually, in sort of normal situations, normal everyday life, only about 11% of the hive is made up of guard bees, which isn't very much when you think about it. So what happens when, let's say, a big bear comes at the hive rather than this tiny little worm? So a massive bear attacking the hive. Well, 11% of the hive of those tiny little bees probably isn't going to cut it. You're going to need more to deter that bear away from the honey. So what the guard bees do is they go back into the hive and they actually recruit more bees within the hive to dynamically switch roles to become guard bees. So nurse bees, undertaker bees, etc., they can all dynamically and elastically switch depending on the load to the system, so depending on how big the attacker is. So bees have this amazing capacity to be extremely elastic when it comes to resource allocation. So by increasing the number of guards, they can then deter away a larger predator like a bear. Once that predator's gone, so once the load to that particular part of the system has decreased, they can then switch back to the original roles they were doing and continue on as normal. So bees are extremely elastic in this regard, and we want our applications to mimic this elasticity when it comes to resource allocation. So as I said, this does all relate to software, I promise. So these behaviors actually all link really well to something called the Reactive Manifesto. So the Reactive Manifesto was a specification created back in 2013, which essentially lays out the core principles needed for building reactive systems and applications. Now it's based on 4 key cornerstones, and I'll take you through each of those and how it relates to the behavior. So the first cornerstone is responsiveness. So it's all about being able to react as soon as possible and be responsive to any events or actions that happen on the system. This relates to the first example and the first behavior I showed you, where the bees are able to respond really rapidly to those instructions on where the food is. And we want our applications to be able to do the same. If a user clicks or creates an action on a particular part of the application, we want our application to be as responsive to that action or that event as possible. To achieve this, there's 2 other cornerstones. So the first of those is elasticity. So this relates to the example I just showed you in terms of the guard bees encouraging other bees to elastically change their role to deal with that fluctuating load on the system. And we want the resources and the components within our application to be able to elastically scale in the same way to deal with fluctuating load. So for example, if I have a restaurant app and I've got loads of people trying to book a table, but no one paying, for example, I want to be able to dynamically change my resource allocation to better deal with the huge load on the book a table service in comparison to the relatively small load on the payment service. So we want our applications to be as elastic as possible to be able to allocate enough resources to the areas of our application that are sort of heavy in terms of load, and also to be as cost efficient as possible. Now, the second cornerstone that enables responsiveness is resiliency. So this links in really well with the behavior that bees exhibit when they have potential failures such as the queen dying. We want our applications to exhibit as much resiliency as the bees do. So we can't, as software engineers, predict every potential failure our application is going to sort of encounter. So instead, we need to build into our applications this inbuilt resiliency to be able to continue despite potential failures happening. If you don't build in resiliency and your application completely crashes or fails or goes down, then you're not going to have an application to be responsive. So resiliency is a really key cornerstone to these principles. Now, these 3 cornerstones and the Reactive Manifesto and reactive systems in general are all underpinned by one key cornerstone. You can maybe tell by the picture in the diagram, and it's the same thing that underpins all the behaviors happening within the beehive. And that's having this asynchronous, message-driven form of communication as its backbone. So the bees are able to communicate both on a one-to-one level, but also on a one-to-many level asynchronously. So when the guard bee comes in to ask other bees to switch roles, they don't individually wait for each bee to go, yeah, I will switch roles, give me a minute. Instead, they just broadcast the message and they know that those bees will respond to it. It's the same with the scout bee. When the scout bee tells them about this food source, it doesn't individually go to each individual bee and check that they got the message. Instead, it's able to just broadcast the message and know that those bees will respond in the appropriate manner. And we want this in our applications. We want this asynchronicity so that we can completely decouple the components of our application and create this non-blocking, truly reactive system and application architecture. So, is reactive architecture the future of application architecture? Well, I think it's probably a good avenue to explore. It seems to solve a lot of the issues we're currently facing with our applications today and helps us meet users' increased expectations and demands. So reactive architecture is definitely an avenue that we should explore when it comes to the future of our application architecture. But how do we actually build a reactive system? So systems nowadays are usually built up of these individual microservices, but each microservice also has to communicate with other components and other microservices within the system, as well as communicating with maybe external systems as well. So we need to think on multiple levels when we're thinking about building a reactive system. So the first of those levels is the individual microservices themselves. And for that, you can use a paradigm called reactive programming. Now, reactive programming essentially focuses on the internal logic within those microservices. So it enables asynchronous flow control within that microservice. But as I said before, our microservices aren't just about sort of the individual microservices themselves. Our applications have a bigger scale, right? So we have to think about the larger scale, so the larger level. So we need to think about how our microservices communicate with each other, how they're communicating with their data layer, how they're communicating with maybe external systems or applications. And that's where this reactive architecture or reactive systems idea comes into play. So let's take a look at reactive programming. So here's a basic definition of reactive programming. It's essentially a technique used for managing internal logic flow within a microservice. So it's all about encouraging this asynchronous form of programming. And it's a great tool to use when you're building microservices and you want them to be as responsive and non-blocking as possible. So there's a fair few patterns that you can use when you're building your microservices to really enable this asynchronicity and this non-blocking nature. So they include things like futures, reactive programming libraries, and reactive streams. So futures you've probably come across before. It's essentially a promise to hold the result of some operation until that operation completes. Then you've got reactive programming libraries, and that's all about encouraging these asynchronous event-based programs. So that includes ones like RxJava or Small Mutiny. And then you've got reactive streams. So reactive streams is all about handling asynchronous data streams in a non-blocking manner, while also providing back pressure, which we'll go on to later. So this is how you can use these patterns to really enable asynchronicity and reactivity within your microservices. But what about reactive systems? Where do these two meet and how do they work together? So let's take a look at our Bs again. Now imagine you've got a team of footballers, and you've got two teams. One is the reactive programming team and one is the reactive systems team. Now, the reactive programming team is essentially a team completely made up of Lionel Messi. Now, he is arguably an extremely good football player, but he may be the best scorer, the best tackler, the best dribbler, but he's never played with any of the other Lionel Messis on the team. So as a whole team, they don't know how to react or respond reactively and efficiently to what the other players on the pitch are doing in their team. So as a team, they're not able to work together very efficiently. Now let's imagine we have a second team. This team is, again, made up of only Lionel Messis, but these Lionel Messi replicas have played together for years. They're able to know exactly how to respond to the set plays that are happening. They know how to respond to the specific sort of skills that the other players are showing and demonstrating. And it's this that is reactive systems. It's all about how they interplay together as well as perform as individuals. So reactive programming, as I pointed out, is a fantastic tool when you're building reactive systems, but you can't just stop at reactive programming. You need to think on the larger level of reactive systems and how those components interact with each other and external components and the data layer. So reactive systems really puts this emphasis on sort of giving us the tools to tackle resiliency and elasticity within the distributed system, while reactive programming is really around enabling data flow transformation to be asynchronous locally within the components. So by using reactive programming, we can enable reactive systems. So my one cringy joke of the whole thing, I couldn't avoid it. How does reactive architecture achieve this behavior? So let's take a look at some of the patterns that we have within sort of the reactive architecture and reactive systems level that many people use when implementing sort of reactive within their applications. So the first of those, and it's one of the most commonly used patterns when you're building reactive applications, is event sourcing and or CQRS. So event sourcing is all around basically ensuring that the changes of state to an application are stored as a sequence of events. So they're stored as this like a mutable log of events that you can then refer back to. And if any state updates again, a new event will be created and added to that sequence. CQRS stands for Command Query Responsibility Segregation. So it's all about separating out the read and write of your application. So the commands and queries. You can apply event sourcing on top of CQRS in order to persist each event on the right side of the application. And actually, bees already enable this. Bees already do this. So each brain of the bee is essentially the local database. So when bees are writing to the dance floor, they're writing to the bees' brains when they're dancing on the dance floor. Now, that means that bees can essentially query their own brains when they go to visit the plant. So if they're knocked off course at any point, they can revisit that local database in their heads, their brains, and find out exactly where the flower is. So it enables this really high availability of information, and it enables this persistency as well. So the two work really well in collaboration and enable this great responsiveness from the individual components of the system. Then you've got a pattern called sharding. So sharding is all about separating out very large databases into smaller, faster, more manageable parts. So we call those individual parts data shards. A shard essentially just means a small part of a whole. So the idea of this is to essentially make very, very large databases more manageable, and it enables things like greater parallelism without collisions in terms of trying to access that data point. So if you imagine with bees, again, bees already do this, they're amazing. So bees, let's imagine instead of the awesome honeycomb structure that they have, instead they just have this one massive vat of honey that they're pouring it into. Now what that means is, as one bee is pouring in the honey, no other bee can pour in that honey because they have to queue behind him. Now that means that you're wasting resources and it's not as asynchronous, and it just means that you're essentially locking in your data in place. So in order to achieve greater parallelism, they've split it out into this honeycomb structure so that different bees can visit different parts of the honeycomb and dump their honey. So it's a lot more asynchronous in that regard, and it enables this parallel processing across the cells, reducing contention. So in this regard, sharding helps enable sort of elasticity in terms of scaling and responsiveness so that they can all access the data when needed. Then we've got back pressure. So back pressure is a form of feedback or flow control. So it essentially enables bottlenecks to be sort of eliminated as much as possible from your system. So it stops blocking as much as possible, which is exactly what we want to achieve with reactive applications. We want them to be non-blocking and reactive and responsive. So let's go back to our bees. Again, this time we've got a queue of bees trying to fill up the cells. But unfortunately, our builder bees haven't been able to build enough cells for them to fill up. So they're now full. So instead of sort of letting the queue form and get bigger and bigger and bigger and wasting all of those scouter bees as resources, instead what they could do is provide feedback saying, you know, as a subscriber to that data, to that honey, I can't cope with the amount of honey that you're giving me. So could someone come and help me build some cells? Could someone come and help us over here? Otherwise you're going to have a huge queue of bees waiting to dump their honey. So this feedback enables subscribers to communicate with publishers to slow down the publishing so that they can keep up and so blocking doesn't occur. And it doesn't lead to a potentially catastrophic failure where you start losing parts of the system because they can't cope with this amount of sort of data or events being published. So it's a really important feedback mechanism that allows systems to gracefully respond to load instead of just collapsing under it. So it's all about sort of enabling this resiliency within your application. And then you've got circuit breaking. So circuit breaking is essentially a technique used to protect resources and to help them recover if they're under extreme load or stress. So circuit breakers usually open when a particular type of error occurs multiple times in a short period within an application. And an open circuit breaker prevents any further requests being made of that service, giving it the time it needs to recover and respond. So with bees, now bees are intelligent beings, so it's not exactly a one-to-one analogy here, but with bees, when they get sick, for example, they can diagnose that they're not sort of performing at the level that they should be. So instead what the bee does is it takes itself away so that it doesn't harm any of the other bees within the hive. Once it's recovered, it can then come back to the hive and restart up with the jobs it was doing before and take on its responsibility again. And it can essentially take more requests. That's exactly what we're trying to do with circuit breaking. We're trying to give that resource or that microservice time to recover and get better again so that it can then perform as it once was. This again is building in that resiliency into your application in the face of potential failure of that resource being overloaded with requests. Now, all of these patterns essentially enable this high availability, but it does come at a cost. It essentially means that if you know the CAP theorem, you're now getting eventual consistency, which is actually more representative of the way the world works. So, for example, for anyone who hasn't seen my talk, you may not know that my mum is the one who draws all these bees. I can't take any credit, unfortunately. And so now when you go and tell your friends, oh, I saw this presentation about bees and systems and reactive, and her mum draws the bees, you can then update them. But until that point, they weren't consistent with the state of sort of the world in that regard. So we live in an eventually consistent world where we're all trying to catch up with the consistency. We don't always have the most up-to-date information available to us. And so actually having eventual consistency isn't the end of the world, because we're able to have that high availability, and eventually, given enough time, all nodes will become consistent with the state of the system in this regard. So it's not perfect, but there are tools and patterns and ways you can implement those patterns that can sort of reduce it as much as possible. But this trade-off is necessary so that we can provide that really responsive service to our users. Now, do you have to go this alone? Absolutely not. So there are reactive frameworks and toolkits out there for you to take a look at, and all of the ones on this chart here on this deck are open source. So if you did want to go and have a play with it, you absolutely can. So they work on sort of different underlying technologies. So just take a look into sort of how each one is optimized or works, and maybe do a bit of research beforehand so you can see which might fit best with the application style you're already using for your applications. So Vertex, for example, is built upon something called verticals. It includes a distributed event bus, and it runs in runtimes like Quarkus. MicroProfile is an open source specification that offers APIs like reactive streams operators and reactive messaging. It's actually used by multiple different vendors, including things like OpenLiberty, Pyara, and it enables asynchronous communication between the microprofiles using those APIs. And then you've got things like Akka, Play, and Lagom, which are open source frameworks based on the Acta framework, which is a slightly different way of thinking about your application architecture. And then you've got things like Project Reactor. So if you're already using things like Spring, that might be a good reactive framework to explore. As I said, these are all open source and you can explore them all afterwards if you'd want to. So why is any of this important? Does it really make that much of a difference? Well, here's a real life example. So it was Verizon, and they were essentially redoing their website and their mobile application. So as you can see here, they have a huge number of visitors and traffic to those applications, and it's a really important point of sale for them. As you can see, 48% of digital sales came through mobile devices. So it was really important that they get their website having a user experience that was as good as possible. To do this, they then switched their previously monolithic application to microservices and made it reactive using some of the Lightbend stack, so Akka, Play, and Lagom. And it made a huge difference. So where they were once going down during Black Friday and they were unresponsive, they now had these hugely responsive applications that were running on 1/8 of the infrastructure. Their developers were more productive, and they were getting more sort of conversions to actual sales by improving their user experience on their application. So you can see here, this is just one example where it really does make a difference, both for developers and for the users involved. Now, we recently, myself and my colleague Kate Stanley, refactored our Kafka starter app to be reactive using Vertex. And if you're interested in seeing this demo application and seeing how we were able to re-architect it, this is the GitHub link to it. And we wrote a whole article talking about our experiences and how we found moving to reactive and the benefits it gave us. So you can check that all out here at this link where we've written up our findings. If you wanted to get hands-on with reactive and maybe try a bit for yourself, you can try these literally 15-minute labs. So the first one uses MicroProfile reactive messaging, and the second one is using microshared testing to test that same application. So you can check those out by visiting the URL here. So those resources will hopefully help you to understand how sort of myself has re-architected an application and how you can maybe get hands-on and get to know those sort of how reactive works and how you can maybe implement it in your own application. For some more useful resources, here are some really good links. So the first one, if I haven't already bored your head off about reactive, you can go to that reactive report. It's a really short ebook that you can read, which basically summarizes a lot of what I've said here today. Then you can go to the Getting Started with Reactive article, which is essentially an article on IBM Developer with some really useful links to sort of other articles and other sort of tutorial series and links to blogs, which better explain reactive and help you get started with it. Then you've got a reactive programming interview. So if you guys know Mark Heckler, then you can check out his interview with one of our developer advocates around reactive programming, RX Java, Spring Reactor. Or you can check out some of the MicroProfile and Quarkus links that I put up here if you're interested in some of those technologies. So thank you for listening. Hopefully I've convinced you that reactive systems is the way to go forward in terms of at least trying to get your applications as responsive and non-blocking as possible to really enable that amazing user experience from your applications and to make them as cost efficient and as responsive and reactive as possible. If you did have any questions that you aren't able to answer in the next Q&A, then feel free to reach out to me on Twitter or connect with me on LinkedIn. Thanks very much.